Thank you, David and Susan, for that kind introduction. It is an honor again to present at the Organization of Human Brain Mapping. In the past, I've been fortunate enough to attend this great meeting as a student, as a postdoc, and several years ago as a young independent investigator. For today's lecture, I'll be presenting on behalf of the Adult Aging Brain Connectome, AABC. This talk will be giving an overview of the AABC with subsequent talks discussing processing methods as well as exciting early results. Here are my disclosures and funding sources. As you can see, I have no links with industry. The highlighted grant in red is the AABC. So our outline of the talk will include a brief history of how we got here and what the AABC will be conducting. To do this, we really need to understand the trajectories of aging and what is healthy versus what is a disease process. We will be also discussing how we get there through both projects and cores. I will introduce the great team that we have assembled, and then we'll go through some of the variables that will be collected. Finally, I will show you some very early preliminary results based off of data that's been previously collected through the HCPA. So the foundation of the AABC started over 12 years ago when approximately 1,200 healthy adults ages 22 to 35 years of age were scanned at Washington University in St. Louis and University of Minnesota using a revolutionary set of imaging techniques that became the HCP protocol. All scanning was performed on Siemens 3T scanners. This was followed by the LifeScan project in 2016 that either concentrated on younger individuals, but also 1,200 older adults ages 36 to over 100 years of age. This became the HCPA. Scanning was again on a 3T Siemens scanner at Washington University, University of Minnesota, as well as MGH, Harvard, and UCLA. For about half of the participants, a second follow-up scan was performed. Scanning was similar to the HCP young adult and was about 90 minutes in length. From this, then a connectome revolution occurred, including one looking at the baby connectome and connectomes of disease. AABC is the next iteration of the HCPA with some twists though. So for AABC, it's based upon many of the original participants that have been previously followed by the HCPA. For AABC, all participants will be scanned twice, about 2 years apart. In particular, 350 of the participants who have been followed for a single time point will be invited back to AABC. This will allow us to have potentially 3 scans on these individuals. In addition, 525 participants who were scanned twice in HCPA will also be scanned for 2 additional time points, allowing us to potentially have 4 time points for these individuals. Finally, 125 individuals will be recruited, will be new to the study and will be scanned twice, and thus will allow us to have 2 time points on these individuals. Now, 3 general hypotheses really guide the AABC projects. Number 1, integrity of the connectome, both structurally and functionally, is fundamental to healthy aging. And when there are disruptions in brain connectivity, this underlies disease such as those seen with Alzheimer's disease or AD or ADRD, Alzheimer's disease and related dementias. Now, there are multiple factors, including genetic, behavioral, social, cultural, and environmental, that converge to predict an individual's resilience or vulnerability to pathology. And there are then key pivotal transition phases or key inflection points that occur during the lifespan that may lead to a divergence in trajectories. And that may be affected by menopause in women, both midlife in men and women with health vulnerabilities, and later life where resilience or resistance to factors that could lead to Alzheimer's disease or ADRD. Understanding these potential changes in brain trajectories associated with aging prior to the onset of ADRD is critical for any treatments that we think for these diseases. Now, we must understand that it's important to know that cognitive impairment seen with ADRD is considered to be a condition of late aging, but the effects and factors that occur across the lifespan ultimately determine when an individual's late life risk will occur. So the AABC consists of 4 projects. With these projects, there's significant interaction. Project 1 studies the effects of allostatic load and immune function and dysfunction during early adult life. Project 2 studies the lifestyle behaviors, either physical activity, sleep, and metabolic syndrome during mid-adult life. Project 3 studies the effects of menopause and vasomotor symptoms during the midlife period. Finally, Project 4 studies the resistance against AD and ADRD in the late life adult period. Overall, all of these projects, as seen in the center, link together to begin to understand how vulnerability and resilience factors affect brain function and structure and how they relate to AD biomarkers and ADRD. So we have been very fortunate enough to have both projects as well as cores, and they are interacting in AABC. Cores will supply the key data to each of the projects and ensure appropriate analyses are performed. Cores include an administrative core, an integrated data acquisition core, an informatics data analysis and statistics core, and a genetics multiomics core. As seen on the right, data acquired from each of the 4 acquisition sites will be fed to the various cores, and then these results will help each of the projects answer key questions that are fundamental for understanding differences between healthy aging and pathology. As you can see here on our leadership groupings, you can see we have a true powerhouse of leaders in the field who will be involved in this project. The project consists of multiple PIs as shown on the top. In addition, there are leaders for each of the projects, which are shown in the middle. And then finally, there are leaders for each of the cores, as well as we have a diversity recruitment and retention unit as shown below. Here's the general overview of the evaluations to be performed for a participant. There's both a pre-study, a visit day, and a post-study material. The general flow is very similar to what was previously performed in HCPA, but there are some notable additions. Here are some of the variables that will be collected at our pre-session, including eligibility measures and clinical interview material. Here's a list of the variables, and it's a very long list, and I don't expect you to be able to read through all of it. But these are the kinds of variables that will be collected when a participant visits us for a scanning visit. We will be collecting both blood and plasma, and we'll also be performing cognitive testing, as well as you can see a number of other tests, including even odor tests. Due to its length, some of these tests could be conducted over multiple days. And with regards to our imaging protocol, here are the variables that will be collected when an individual visits us. As you can see, there are 2 scanning sessions on a 3T Siemens scanner. Multiple imaging techniques will be acquired, including resting state structural scans, functional tests. In addition, at MGH and University of Minnesota, for those individuals who want to, they will have the opportunity to have 70 MRS performed. But again, this is optional. Now, you will see in subsequent talks results regarding our processing streams for neuroimaging that will be discussed by Dr. Klasser, as well as functional imaging results by Dr. Rashid, and then MRS results that will be shown by Dr. Terpstra. Now, here are a list of the variables that we'll be collecting at the post-visit session, often at home. These include actigraphy, vasomotor monitoring, and a food diary questionnaire. Now, using this, our data analytics and statistics core will provide state-of-the-art tools for the projects that will help us conduct association modeling, accounting for longitudinal structure. They will also test for differences in structural models using pro-specific mediating influences and associations. And then they will try to reduce the dimension summaries from large numbers of related variables, as I showed to you before, and then work with imputing missing data using a unified approach. The goal will be to build models that will allow us to predict health outcomes. Now, using all of that, we've been already starting to able to start collecting very exciting new information. Here are preliminary results. On the top left is the distribution of perceived stress scale scores, are highest in HCPA young participants who are 25 to 50 years of age. On the bottom left, you see perceived stress was correlated with allostatic load proxy, so a measurement of how much factors or influencing, outside factors are influencing these individuals. On the right-hand side, we see age-corrected associations of functional connectivity with stress and allostatic load, and they were seen with regards to the default mode, amygdala, and hippocampal networks. As you can see, with increasing perceived stress, the posterior cingulate and amygdala are more strongly coupled with connections between the somatomotor cortex and the amygdala, while connections between the somatomotor cortex and the amygdala are reduced. With increased allostatic load, connections between the medial cingulate, frontal, and nodes of the default mode network are also strengthened. So overall, we're starting to see that allostatic load can both affect cognitive performance as well as functional brain networks. Now, in regards to one of our other projects, we also looked at the effects of menopause, and particularly differences in anti-correlations between the default mode network and task-positive network were seen with regards to menopause transition stages. So either in pre, peri, or post, and you can see in post, there is the greatest anti-correlations between these groups. In particular, anti-correlations were greatest in the post-menopause group compared to the pre-menopause group. In regards to the right, we also started looking at these in relation to AD biomarkers, in particular plasma biomarkers. So comparisons of plasma A beta 42 to 40 for early versus late menopause stages. You can see women in the late post-menopause stage had significantly lower A beta 42 plasma levels. So they already started to have more preclinical signs. So this suggests to us is that menopause is associated with changes in brain connectivity and Alzheimer's disease biomarkers. Well, here's the great group of our team, and we wouldn't be able to do this without such a great team. I'd just like to highlight our project manager, Angela Oliver, as well as all of our great staff, as you can see on the right, who are key to this project. I want to thank everybody for their attention, and I will go to our next speaker.